Right, so we're going to now look at how we use BSP trees to do what we call visibility ordering. This is how they're used to actually remove the hidden surfaces. And essentially, it's Painter's algorithm. We can use BSP trees to determine the rendering order for the Painter's algorithm. Now, if you remember, the Painter's algorithm was all about you taking the distance from each polygon and you're sorting them into descending order in terms of the distance, that Z distance. That's all very well and good for the Painter's algorithm, but for that, you've got lots of calculations every time you move the camera position. And lots of calculations generally bad for graphics applications. BSP trees, this is one of my favorite things about graphics, one of my most favorite graphics application. The BSP tree is independent of the viewpoint. It doesn't matter where the camera is in your virtual world, the BSP tree is always the same. So only one BSP tree is generated for each virtual world. So you don't have to do that again. You do it once, and then that's it. Now what we do is we traverse the BSP tree using whether a node is front-facing or back-facing to the viewpoint. So we do what we call a tree walk. If a node in your BSP tree is front-facing, i.e. the person who's at the viewpoint should be able to see the front face of that node, all polygons behind that node are further away from you, because then they're behind it. If you're looking at the back of a polygon, all polygons which are in front of that node are further away, and all polygons behind are closer. So whilst we're not calculating the distance, we do know whether something is closer or further away than something else. Okay, so here's our example. This is from the last lecture. I had a virtual world with the 4 original polygons, A, B, C, D, and in it, at one point, I did cut across A and created 2 new polygons. And that was my tree. Okay, so what if we have a camera positioned at P? That's our viewpoint. We use what we call an in-order tree walk. I'm not going to dwell too much on that because it's a lot more complicated than it actually is. So, yeah, actually, that's all I'm going to. You've got it in your notes, okay? That's a sort of official algorithm for it, but it just looks more complicated than it needs to be. It's a lot easier than that. Here's an example, and I'll work through it. What we do is we start at the root node. So this is root node C. There's that node there. And we ask, is P looking at the front or back of C? Now in this case, it's looking at the front. So what that means is we do the opposite. If we look at the front of a node, we go to the back subtree. So we're at C, we check C, we're looking at the front of it, so we go to the right-hand node. And then we check B. We move to B. B is back-facing. So if I was to draw an arrow from P to B, we'd be looking at the back of it. Because B is back-facing, we go to the front child. So we kind of do the opposite. We check which side we're looking at. If we're looking at the back, we go front. If we're looking at the front, we go back. And we keep doing that until we get to a leaf node, which we have done here. We're at A1. The rule is, when you're at a leaf node, you add it to your rendering list. This is the order in which we're going to render these nodes. So I add A1, and the rule is you immediately add its parent if you haven't already added it. So in this case, I'm going to add the node A1, and I'm going to add B, because B is A1's parent. The only time I don't do that is if B has already been added. We never add a node. Okay, so we do the opposite. So if it's front facing, we go back. If it's back facing, we go to the front until we get to the bottom. Once we're at the bottom leaf node, we add it, followed by its parent. And then we go to the other child node. Okay, so we're at the so we've added A1, we've added B, and we've gone to the other child node. A2 in this case happens to be a child node. So the rule is we add it, followed by its parent. But its parent node B has already been added. So we go up to its grandparent node C, and we add that. If we can't add the parent, we add the grandparent. If the grandparent's already been added, we add the great-grandparent. So our current rendering list is A1, B, A2, C. And then we go to the other child node from C. D is a leaf node, so we add it. Okay. Now we've added all of our nodes from our tree. That gives us a rendering order. Okay. So this is my rendering order. If I was to render these polygons in turn, I'd add A1 first, then I'd add B, then I'd add A2, then I'd add C, then I'd add D. So you can see that rendering order has gone from pretty much the furthest to the closest. Without having to calculate any distances, all we've done is walked around our tree. It's very, very efficient. Guy who invented this, guy called Michael Abrash. Have you heard of him? He formed ID Software. He invented Doom. No, nobody played Doom? Early mid-90s?
I don't play that.
Doom, don't think, did they do Quake? I don't think they did Quake. They did Descent. So very, very sort of mid-90s. Actually, sorry, he wasn't the guy who invented it. Schumacher did in '69, but he used it in computer graphics, so I should make that correct. But in all of this, all we've done is looked at dot products because we're testing whether something's front or back facing. Dot products very, very easy to calculate. We haven't had to calculate anything difficult. Okay, right. So now we're going to